For more than a century and a half, the Riemann zeta function has stood at the center of mathematics. It encodes the prime numbers. It satisfies a mysterious symmetry, the functional equation relating s to 1 minus s, and it guards the deepest open problem in the subject, but there has always been a stranger question underneath. Where does a zeta function actually come from? We usually attach zeta functions to spaces, to number fields, to graphs, to manifolds. Zeta space begins with a different idea. Zeta space was built as a tool for understanding zeta functions, not by manipulating the functions themselves, but by constructing a geometry that generates them. The guiding intuition is simple. If a zeta function behaves like a spectral trace, like the sound of some hidden drum, then instead of studying the sound, we should build the drum. Over the years, this project has produced many constructions: analytic generators, foliated completions, an interface surface, a seam graph, a symmetry group. This post reorganizes all of them under a single functorial viewpoint. The claim is that beneath every one of these constructions sits one abstract object, a seed. Here is the basic philosophy in one line. The zeta function is not the seed. It is a trace of a realization of the seed. The basic object of the theory is not a function at all. It is a geometric seed, s equals I gamma pi. The project did not start here. Earlier versions began with two analytic generators, phi s of x equal to e raised to s over log x, and phi t of x equal to e raised to t over log of 1 minus x. Zeta space was first imagined as the interaction of these two analytic families, exponential kernels whose Mellin transforms produce Bessel functions, and hence a natural spectral world related to zeta functions. The next step lifted these analytic leaves into geometry, an F completion, built from foliations whose leaves accumulate at pairs of boundary vertices of a block. Inside this completion, the special object appears. I is the interface object, a symmetric interface in dimension 3, obtained from 4 maximal surfaces of revolution inside the cube, each with constant positive Gaussian curvature and cone points at antipodal boundary vertices. Gamma is the distinguished degeneration locus, and it is not an auxiliary graph added afterward. It is generated by the interface itself. Slicing by the coordinate midplanes produces overlapping oval curves, and their intersections assemble into gamma. Gamma is where the geometry becomes combinatorial, and where the combinatorics become spectral. Pi, finally, is the symmetry data acting on the seed. Here is a concept of a decorated seed. The white chassis represents the uncolored part of the interface. The colored bands represent a stratification of gamma, and the arrows represent a local system. But keep this in mind, a seed does not actually look like anything. It is an abstract object. What you can do is extract information from it through its realizations. Zeta functions and their twisted versions are traces taken over a given realization. So the right language is not symmetry of the interface. It is realization of the seed. Let seed denote a category whose objects are these triples, possibly enriched by a coloring of gamma, a local system, and a holonomy representation. Several realization functors then send the same seed into different worlds. The geometric realization remembers the interface. The gamma realization remembers the skeletal degeneration locus. The holonomy realization remembers flat line bundles, homomorphisms from the fundamental group of gamma into U1, modulo the symmetry data, and the zeta realization sends holonomy data to a twisted Ihara-type zeta function, a product over primitive closed paths in gamma. This clarifies the role of the delta groupoid. A delta morphism may preserve the underlying graph and even the untwisted Ihara zeta function while transforming the enrichment data. The coloring, the local system, the holonomy class, so the delta groupoid acts not merely on gamma but on the category of enriched realizations of the seed. The graph stays fixed, the realization changes. The functorial viewpoint separates 3 layers: seed, realization, trace. This viewpoint matters most for theta modularity. Classically, the theta function, a sum of Gaussians over the integers, satisfies a striking identity. Theta of t equals t to the minus 1/2 times theta of 1 over t. This is not caused by an ordinary geometric involution of a space. It is caused by Fourier-Poisson duality. The Gaussian at scale t transforms into the Gaussian at the dual scale, so in the seed formalism. Theta modularity is not a rigid map from the interface to itself. It is a natural transformation between two analytic realizations of the same seed. The cone localized realization, built from radial and angular modes near the cone points, and the dual of the gamma organized realization. Now the completed zeta function arises as the melon transform of a theta trace. Split the integral at t equals 1. The small time part corresponds to the cone localized realization. The large time part corresponds to the dual gamma organized realization. Theta modularity identifies these two regimes, and after the melon transform, this realization level duality becomes the functional equation. Lambda of s equals lambda of 1 minus s. So the symmetry s goes to 1 minus s is not primarily a symmetry of the complex plane. It is the melon transform shadow of a Fourier-Poisson duality between two realizations of the seed. In this picture, the seed is the object, the zeta function is the trace, and the functional equation is the shadow of a duality between realizations. The early PDE construction supplies the analytic generators. The F completion supplies the ambient space. The interface supplies the seed geometry. Gamma supplies degeneration and holonomy. The delta groupoid supplies the enrichment dynamics. The twisted Ihara-zeta function supplies one trace realization. And theta modularity supplies the natural transformation between cone and gamma realizations. A zeta function is not attached to a space alone, but to a realization of a seed. Zeta space is a theory of seeds, realizations, and traces. This is the functorial form of zeta space.